Hello to everybody. Please sit down. We will start this new Friday colloquium, and it's a pleasure today to welcome Stanislav Babak, aka Stas Babak, who is currently the head of the group of gravitation at Laboratoire d'AstroParticule et Comologie, APC. And he is actually director de recherche there. Stas defended his PhD thesis in 2000 in Cardiff about relativistic astrophysics under the supervision of Leonid Grishuk. And then he became postdoc working in the context of GEO 600, you know, the German interferometer, which is a kind of benchmark. And this was between 2001 and 2005, roughly. He next moved to the Albert Einstein Institute in Golm, near Potsdam, where he was hired as a research scientist and then later senior research scientist. Between 2005 and 2017, which is when he was actually hired as directeur de recherche at APC. It is difficult to describe his research interests. They are very broad, almost everything about gravitational wave astrophysics. It goes from, for instance, instrumental calibration uncertainty to modeling gravitational wave from exotic compact objects. But more generally, this goes from data analysis, sometimes very specific and technical things, to what we can learn from detections, what are the constraints this will put, and what it will tell us about the astrophysics of, for instance, binary black holes or other things. And this is why Stas is actually a member of many gravitational wave collaborations. For instance, the Virgo collaboration, the Einstein Telescope collaboration. He's member of the LISA consortium. In fact, he was the chair of the LISA Data Challenge Working Group until quite recently. He founded this group in 2017. And very recently, last year, he was also the chair of the International Pulsar Timing Array Committee, which is very relevant for the topic of today because Stas will be precisely talking about search for gravitational waves with Pulsar Timing Array. So Stas, you have 1 hour and the stage is yours now.
Thank you very much. Thanks for introduction. Thanks for inviting. And I hope to entertain you about indeed PTA today. And well, let's move, right? I will be using, I guess, this, right? So it will be easier for recording. So that first I want to just briefly introduce the gravitational wave landscape, and there are 3 major projects in 3 different frequency bands. One on the ground, it's where advanced Virgo and LIGO operating and currently taking data as a 4th observational run. Then there is in mid-frequencies LISA, and we are very eagerly waiting for its adoption at the end of this month. And when project really start to be built and exist as a proper project within the European Space Agency. But today I will be talking about even lower gravitational wave frequencies. It's a nano-Hz band, and there we're using Pulsar Timing Array trying to detect gravitational waves in this band. I'm not going to describe what the pulsars are. Just very briefly, for us, we're using pulsars as a clocks. And the best clocks are the millisecond pulsars. So these are old neutron stars. Anything could happen to them already happened, and they just behave as the very regular clocks. What I mean by clocks is means they have very stable rotation. And the beam radiation, which is coming from magnetic cups, sweeps across line of sight. And we see this kind of set of pulses, which you can see here, as a beam goes across the line of sight of radio telescopes. And milliseconds is basically corresponds to the rotation period of these pulsars. Each pulse, which is observed by a radio telescope, has a microstructure which reflects the magnetosphere of the neutron stars and internal processes. But if you're averaging all these pulses over, let's say, 1 hour or so, it has very stable shape, very stable structure. You can see it here. And that's what is called template profile. And this is what is used to understand time of arrival of individual pulses. And as I said, each pulse arrives at very regular intervals, but not exactly regular, okay? And there is a small deviation between what you would expect from the absolutely regular arrival time and what you observe, and that's what is called residuals, and what we will be talking about. So this is the time difference between what you expect and what you actually observe. And there are many reasons where you could have this difference. I give you several of them. So, for example, if you do not if you don't measure very precisely position of the pulsar on the sky, you will have residuals which have period of 1 year, this annual modulation of the residuals. If you make an error in the how fastly or let's say period of the rotation of the pulsar, then you have this linear trend, of course. And if you then take into account rate of change of spin, because the rotational energy gets transformed into electromagnetic energy, and millisecond pulses spin down very slowly, but nonetheless they do. And then if you don't take this into account, yeah, exactly. And then you have this quadratic shape. And if you don't take into account proper motion of the pulsar, you will have, again, annual modulations, but growing in time because you don't take into account the shift of the position when it's growing. Millisecond pulses quite often are in a binary. Actually, most likely they all were at some point in a binary system. And that's how they get this fast rotation through the accretion. And if you then take into account the orbital motion within the binary system, then you will have this modulation with the period of the orbital period of the binary system. And of course, another important element which we need to take into account is dispersion, because radio emission propagates in interstellar medium. There are a lot of electrons floating around, and there is a kind of almost constant dispersion, but at the same time, there is also dispersion changes, it's variations in dispersions due to line of sight between us and the pulsar changing, environment between us and the pulsar changing, and that creates a small variations in dispersion measurements. So we need to take this into account. So there is a constant big shift which we will take into account, and there is then time-dependent dispersion measurement. So if you take all this into account, your residuals should look like white noise, almost white noise. And I will talk about how they will look like and why in a minute. Next, what we're dealing with is not one single millisecond pulsar, but many millisecond pulsars, which are stable, which are bright, and distribute across the galaxy. And that's what we're calling array, and we're taking into account all the observations for all the pulsars, and we concatenate them in a single big array of observations. So if there is a gravitational wave signal coming from somewhere, okay, this gravitational signal will modulate blue and red shifts the pulses. Okay, so it will modify time of arrival of the pulses. Jumping a bit ahead, it's what happens in between emission and the reception of the radio is averages out, and at the end, the main effect will coming from the time of emission and time of reception, similar to integrated Sachs-Wolfs effect, which you probably know, all of you. And if in case of gravitational wave signal to be stochastic, it looks like a noise. and noise in time of arrival of the pulses, okay? But the key point that this noise is actually similar in all the pulses, and that's the main idea of the looking at many pulses and cross-correlating them. And if it's gravitational wave signal, again, I'm jumping a bit ahead, but preparing you, it depends on angular separation between the pulses on the sky, this zeta angle, and it has very specific function, this correlation of how noise looks, similarity of the noise in different pulsar observations depends on the angular separation between each pair. And that's curve called Helling-Downs by authors who first derived this. If you have a monochromatic signal, then it's, or sinusoidal signal, then you will see this kind of going on and off in time of arrival compared to what you expect. This would be deterministic signal in your data. So all in all, the residuals which I introduced, it's a time of arrival predicted minus observed. You need to take into account all the effects which I mentioned before, what's called timing model. There are more effects which need to be taken, including relativistic effects, especially in the binary system. But we don't know exactly the parameters of this, and we might still have small errors, and that propagates into the error in the fitting of our timing model, delta t. Then, of course, the most important for us is delta t coming from gravitational waves and the noise. I want to spend 1 minute on the how response of radio of this Pulsar Timing Array to gravitational waves. And one of the important factor here is the size of your device, measuring device, compared to the gravitational wave wavelength. And this epsilon parameter. So basically epsilon, you can see this as a ratio of size of typical size of the detector to the wavelength of gravitational waves, typically which you want to measure. It is much less than 1 for ground-based detectors, and then response is very simple. It's simply projection of your gravitational wave strain on the arms of your detector. In case of LISA, epsilon goes to 1 right in the frequency band of the detector. If you remember sensitivity of LISA, you will see this sync modulation of your sensitivity. It's exactly because of that. In case of PTA, it's a completely different regime, and this epsilon much larger than 1, and this transforms into the how we see the gravitational wave signal. So what we're measuring, like in case of ground-based or LISA, it's a change in the frequency of your laser in case of the ground-based or LISA compared to your nominal frequency because of the gravitational wave signals. Here, delta nu is not frequency of laser, it's a frequency of arrival of your pulses. So you know how many pulses per unit time you're measuring. And this equivalent to measuring the phase of the laser, but here we're integrating the frequency of arrival. We're kind of measuring phase of arrival of the pulse, ticks and tacks of our clocks. Okay, and this is expressed in terms of again projections, but important part is this delta H, and as I already mentioned to you, it depends on the time of when it was emitted by the pulsar here, pulsar time, minus H at the time of when we observe a radio pulse. And this separation, it's a distance between Earth and the pulsar, and typically it's a kiloparsec. So we're talking about 1,000 years. And therefore, at time of emission, time of reception, we see different parts of gravitational wave signal from the binary system, for example, if you take into account binary system. So they will be at different frequency, etc. So the separation here between different parts of the signal of over 1,000 years, but you see that's 1,000 years, it would be L, but there is also geometrical factor. And this plays important role. So if gravitational wave source right behind the pulsar, you see nothing. It's what's called effect like radio pulse is surfing gravitational wave, so it moves together with the gravitational wave. And this poor analogy, but nonetheless, it's kind of illustrative. Right, and so that's how we have 2 terms, which is called pulsar term at time of emission and time of reception Earth term. So it's 2 parts. I will spend some time on data analysis, how we basically detect the signal, what we're looking at. And again, we're starting with the assumption that our noise is Gaussian, and therefore we formulate likelihood as a Gaussian distribution. And what do you see here? Delta T is this array of our measurements concatenated from many, many pulses. S is a deterministic signal. So this where, for example, your timing model goes into, okay? Or errors in timing model goes into. And it could be also the signal, for example, from individual binary. I will talk about this later. It also goes into this S. So basically any deterministic signal goes into S. And C is your noise matrix. You need to take into account what noises are there. And the noise here, this is decomposition, the most probably not the most general, but nonetheless, it's kind of gives you idea. So the first and the easiest component of the noise is a white noise, and it mainly comes from the measurements, radiometer noise. And this noise is dominant at high frequencies. At low frequencies, we will have red noise. Red is because it's if you look at the frequency domain, it's rising at the low frequencies, and at some point it becomes dominant above the white noise. So the typical noise is basically rising up. I will talk about different red noises, types of red noise in a second. But the most common one is coming from the spin of the neutron stars. Because of the spin is not stable, it appears as this red noise process. Sorry. Dispersion measurement variations, I already mentioned this, is because dispersion is time, there are small time variations on top of the big constant factors. And the most important one is stochastic gravitational wave signal. So I will speak about red noise because that's the most important for us, because the gravitational waves in the pulsar timing array, noise-like sources, we expect to be red-like. And we can separate between two different intrinsic red noise. It could be individual to each pulsar. It could be common to all pulsars. Common, it means that the spectral shape of the noise is common to all pulsars. So it's a noise with a similar shape, okay, with similar properties. Doesn't have to be correlated or doesn't have to be exactly the same. Dispersion measurement variations also looks like a red noise, but it's also, you see in the denominator, it's a radio frequency. So that's where the dispersion comes. So that depends on the radio frequency with which you observe. So the more you need to have multi-band receivers in order to measure this. It's a very important thing. And finally, the most important part is a red noise, which is correlated. So it appears with some correlation similar to each pulse observation. And the gravitational wave signal is of this kind. And this plot here, it's angular separation on the x-axis, and on the y-axis is the correlation. And I start with different, if a noise completely uncorrelated, just common, you expect this kind of random correlation factor, okay? If you have problem with the clocks in your radio telescope, because each radio telescope has its own clock, which is synchronized to atomic standards, then you will have the common error in all the pulsar observations. And that's gives you what's called monopolar or constant correlation across the pulsars. If you make an error in your ephemeris, so basically we're reducing all our observation to solar system barycenter, and if you don't know exactly where solar system barycenter is, and you need to infer this from the ephemeris, which we use either in POP French one or GPL ones, and actually they don't agree very well. It's a different story. Then you will have cosine type of correlation. And finally, if you have gravitational wave, then correlation should follow what is called Helling-Downs curve. And that's what we're trying to measure. We're trying to measure correlation between the pulsars in order to infer gravitational wave noise type signal. I'll skip this, and this. So all in, that's exactly the question we're trying to answer. So we're not trying to understand if the noise we're measuring is gravitational wave or not. So there are different predictions, and predictions go from very high to very low. Up to now, we were setting upper bounds. And that's for first time, which I will talk about, we see something which follows this correlation, and we think it's emerging gravitational wave signal. And I will talk about amplitude in a second. So if you skip deterministic signal, everything is encoded in this noise matrix here. There is a white noise, and there are different types of red noises here. And that's what we parameterize this matrix C red noise. And we're trying to infer parameters of this signal, which is entering in here. Another important thing which we're trying to do is we will apply several models to explain our observations. And here we use a Bayesian approach, and we use what's called Bayes factor. It's evidence ratio of evidence. Evidence that data D, observational data D, is consistent with the model M1 or M2. That's the thing. And we always assume that all the models have even or exactly the same prior, which is not true. Now I'm going into IPTA and the results, and I will try to give you IPTA results, not specifically EPTA. So IPTA consists of nanograph, it's North American collaboration, EPTA, PPTA, it's Australian, around Parkes telescope, and India PTA, around the radio telescope GMRT. And there are two emerging PTAs which are not yet members of IPTA. Is MERCAT, is around the precursor of SKA, and the Chinese PTA around the radio telescope FAST. I will concentrate only on IPTA, so basically on the results from nanograph, EPTA, and PPTA. Indian PTA data is incorporated into European one. That was the agreement. Data. I'll start with probably less exciting to the most exciting. Parkes, Australian data, they analyzed 18 years of data. They have 30 pulsars. And I think it's important information, as you see a bit later. 3 last years were obtained with ultra precise or ultra sensitive new receivers, ultra wideband receivers. All the previous data was taken with a rather old one. What they see is, you can see here, it's a power spectral density which they infer. There's frequency, there's amplitude in some units. And they see basically the red noise process, which is consistent with Hellingsdowns. Of course, consistency with Hellingsdowns, you can see here, it's quite poor. The error bars are quite large. And statistical significance, which they inferred in their data, was rather poor, which brings a lot of questions. But nonetheless, it's constrained. So this, if you look at the gravitational wave part, it's you constrain on the amplitude of the signal and its spectral shape, basically the slope here, but it's still quite broad. I'll come to this plot closer to the end. So let's move on. If you look on EPTA and IPTA data, we looked at 25 pulsars, and data was up to 25 years. And here we had to split data into 2 parts, 25 years, the full duration. And actually, when we looked at full duration, we saw nothing. So Bayes factor for Hellingsdowns was only 4. And the second part is we just took the most sensitive data from the last 11, not 14, I think it was 11 and a half years. What we call DR2 new, it's when all the radio telescopes went up with the upgrade of the receivers and started to time pulses with almost regular intervals, roughly 2-3 weeks. And then we saw the quite not huge, but nonetheless significant Bayes factor like 60 for Hellingsdowns correlation in our observations. And there's just visual how good it is. You can see it here. And it's up to you to judge this number. There is no strictly speaking the scale. Of course, it's thousands and 100,000s you're confident, but 60 is usually referred as a good evidence for. But all the posteriors which we see, this again, amplitude versus the spectral index, and the Hellingsdowns have really big error bars. Okay, it's poorly constrained things, but nonetheless, it's kind of emerging things, I would rather say. It's just that's how the correlation is inferred. So the pulses which separated by 90 degrees should have negative correlation. That's what it is. No, this assumes isotropic distribution of gravitational signals, but not exactly that. I'll come to this when I talk about continuous waves. Probably, I'd never thought about this. Maybe, yes, it's maybe, but it's cross polarization would be different, but maybe, yeah. Yes, here we're talking about background, but interpretation will come in a second because it's not that simple. Yes, that's what it is. This is the correlation of the data of the signal between different. So this angular separation between the pair of pulsars, and that's how correlation which we're inferring in this purple plots, in this purple probabilities. Let's say, if you can look at this as a measurement of correlation between different pulsars in these purple histograms. So you can look at this as a histogram, okay? And the bulge is the most likely, and the tails is the less likely thing. So it's a poorly constrained, but by eye, it may be deceiving a bit, but it kind of follows a little bit of Hellingsdown's curve, which is the green curve here. Now, we want to also quantify how likely it was to get this result. If it's, well, how significant, statistically significant this result. It's very hard. One would do this, making many observations, preferably without gravitational wave signal, and say, okay, there is no gravitational wave signal, noise only will give me this. So you want to preserve noise properties of the observations, but remove gravitational wave signal. We have only one observations. The signal is there. What we're going to do, one of the examples is that we're shuffling artificially pulsars on the sky and redo the calculations. So in other words, observations which we see, how likely it was obtained by random position of the pulsars on the sky. And that's one of the way of seeing and trying to estimate the significance of our result. And in the case of EPTA, it corresponds to roughly 3 sigma significance. Now going to nanograph results, they use 15 years of data and they had 67 pulsars. Of course, not all the pulsars are good, equally good. And there is a hierarchy, a strong hierarchy in the goodness of them. But nonetheless, they see similar results. They see, again, Hellingsdown, they see the power law. And now if you look at the base factor, they have conservative number is 226, so it's significantly better. They claim that it comes from using large number of pulses, so it goes, the number of pulses matters, but it also comes with computational power. The more optimistic number is 965, and if you ask me later, I will explain to you what's the difference between them. And this roughly corresponds to 3 to 4 sigma significance in the results. Okay, so this is probably the most significant from the point of view of gravitational wave observations. Now I'm talking about interpretation, and immediately many people jump to trying to interpret the signal, assuming that it's a gravitational wave signal, where it could come from. And there is a big disclaimer that I give only a few examples, and it's my own personal view and preference, okay? It does not reflect preference of other people. But the thing is, because the sensitivity, current sensitivity is rather poor, and what we found is whatever you throw in, more or less works. So the most natural one would be a superposition from supermassive black holes binaries. So you have two binaries well separated in spiraling around each other for 30 million years. This is a result of the merger of two galaxies. And that's one of the sources. If you simulate your universe in this population, in the local universe, you don't need to go to higher redshifts. You have this cloud of individual sources, which are green points. Why there are points? This frequency, this characteristic amplitude, because at these frequencies, at this separation, the binaries are almost, the frequency, the orbital period of this binaries hardly changes. So it's almost monochromatic signal. So that's why it's almost a point. If you sum them up, because of non-coherent superposition, you will have this red component, which is stochastic component, simply because of large number of individual sources. And sometimes you might have individual binary which sticks about this stochastic component, which you might see it as a hot spot on the sky, as a deterministic signal, sinusoidal deterministic signal. So what about this background or foreground or whatever signal, stochastic signal created by population of the binaries? Can it explain? Yes, it can. So here is an example of nanograph fits and EPTA fits. And here they use two different models. One is simplistic, which is dashed, and more realistic, which is blue. And both models fit rather well into the data. Similarly, we did exercise in the EPTA. The orange are the observations, probability, at different frequencies. And the green are predictions from the astrophysical model. So you see they're rather consistent. And here in the black, it's one of the realization, which actually just by chance shows that possibility of this outburst from individual sources.
Here you choose the spectral index of the gravitational wave background so that it is supermassive black hole.
No, it's really just we took population of the binaries, we computed gravitational wave signal from each binary and summed them up together. So usually it's the two or three. It's typical from the in-spiral. They're all more or less following. No matter what the binary is at that stage, they will follow roughly the same thing. However, this small difference is important. It's because it's not gravitationally wave-driven. At the very low frequencies, the gas and the other stars might influence, and they spiral faster. And so this dashed line is if you purely gravitational wave-driven, and the blue one is if you take into account three-body effect, basic interaction with the other stars. Yeah. Yeah, of course. It's all taken into account how the source is distributed in the redshift. So it's basically you take a model, your astrophysical model, you simulate sources which you get from this, your favorite astrophysical model. And you see which of these binaries fall into Pulsar Timing Array band. You compute gravitational wave signal, which is simple. It's monochromatic signals from each of these binary. You sum them up, and you will get roughly this kind of. Yes, it has constraint coming from observation as well, and from it depends. Okay, so but usually you should respect some of the observations. Right. This is coming from the Rayleigh gravitational waves. It's a tribute to my advisor. It's coming from the early universe when you have primordial fluctuations in very early universe, which would amplify during the inflation, and you could have gravitational wave background similar to CMB. I would say it should be rather here, but it's very broad distribution, but nonetheless, it's still consistent with current observations. Another popular interpretation coming from cosmic strings, from the network of cosmic strings. So cosmic strings form the loops, which oscillate and emit gravitational wave signals. They also could form the kings and the cusps, which propagate on the strings and also emit burst-like signals. So you have popcorn-type noise, Poissonian noise, which could create stochastic signal in the nano-Hz band. And because there are many models of cosmic strings, you might try to set the most popular is this. Cosmic strings are quite simple. They describe by the tension, so energy per unit length parameter, and you can try to infer what would be the tension of cosmic string network to produce this signal, assuming that it's gravitational wave, and you can have constraint depending on your model. Here is EPTA results, here is nanograph results. And this is the plot from Hippolyte. So it shows basically that roughly more or less everything goes because of the poor sensitivity of current data. Now I'm coming to individual source, and that's where things becomes more interesting. So as I said, you could have supermassive black hole binary, which produce like a hotspot on the sky and stands above the background. So that would be monochromatic signal in your data. And if you look at the simulations of the different realization of the universe, You can occasionally see this outburst here. You can see more or less smooth component following the blue line, but occasionally you can see the outlier. This your individual binary rotating around each other and producing signal, which is probably binary was especially massive and relatively close. Closeness, I'm talking about 60, 50, 100 megaparsec. It's really close. And coming back a bit, how a signal looks like. So I told you about Earth term, and Earth term is fully coherent. So it basically it's a sinusoidal type signal, which is at the same frequency in each pulsar data. The same frequency. It doesn't have the same amplitude and phase, and that's where it's interesting, because that's how you get the position of the gravitational wave source on the sky from the phase and the relative phase and amplitude. But then there is a mass coming from the pulsar term, because distance to the pulsars are different, and therefore the pulsar term could be, again, monochromatic signal, but at different frequency with different amplitudes. It might be different from Earth term frequency, or might be the same, which is destroying the coherence. This is unfortunate. I'll start with nanograph results, and I will concentrate on this one. So they see something at low frequencies, this base factor, mildly significant, but if you're trying to explain data only with this continuous wave, in principle you can, and you have estimation of the frequency, this minus 8.4 in logarithmic scale, and its amplitude. However, if you're trying to put a model, background plus continuous with this individual source, that background absorbs, being easier model, simpler model, absorbs your monochromatic signal. Having said that, so this, you see the yellow posterior, this spike disappears. However, if you're trying to estimate signal to noise ratio of your background, just before, like you usually do, assuming that there is only background there, and second time, you subtract your individual source, which you think might be there, and then re-estimate signal to noise ratio of your background, you see the shift from like 3-4 signal to noise ratio to something which is below, consistent with 0. Interesting. And more interesting that in EPTA, we see something similar signal at the similar frequency. And we have very similar result, meaning that if you just use a signal, we see if you're assuming that noise plus this individual binary, we can estimate its position on the sky, which is quite broad, but actually consistent with the Fornax supercluster. And we have similar frequency and similar amplitude to nanograph, but if you include gravitational wave background, then base factor drops to 1, meaning the data is completely non-informative whether the individual binary is there or not. So in other words, we cannot say much about presence, but we can explain the data also well without any background with just one continuous wave. So interpretation is not that simple. And we have also in APTA similar result. If you subtract the signal and then re-evaluate significance of the background, it goes to 0 almost. We did simulation when we just did artificial data with a background and tried to detect it with continuous wave, and we can. Then we did simulated data with only one continuous wave and tried to analyze it with a gravitational wave background, and we can. We're still recovering the signals. So interpretation is not that simple of the data. And we need more pulsars and more data in order to clearly separate and interpret our observations. Am I clear here, or I'm losing you? Let me reiterate, this is an important point. Interpretation as a gravitational wave background from different types of sources is not trivial because of the sensitivity. But there is even more complicated story. In my opinion, we cannot clearly separate whether it was continuous wave, just simple hot spot on the sky, or it was gravitational wave background, or both. And I think we need a bit more data. You need more sensitive data, which is hopefully coming from SKA, etc., MERCAT, even MERTime, to do this. And I will come to this in the conclusion. Now, is it really gravitational wave signal? Let me just play devil's advocate and trying to say, what else could it be? We already saw this, the thing that coming from ephemeris. So that different ephemeris would give us gravitational wave or not giving us gravitational wave. Now we have very good ephemeris called D440, and they're similar in pop ephemeris, which take into account Jupyter data. So Jupyter orbit is quite well constrained, and it brings error on the solar system barycenter to much smaller uncertainties, let's say. So I think it's not ephemeris. Now, what else could it be? Noise. This is important. We have no control of the noise in the pulsars. And the only thing we do, we are modeling it together with the model noise from gravitational wave signal and individual source. And let's take one pulsar. It's a very good pulsar, long observed, 1713, and try to see its noise properties from 3 different collaborations. And they don't really match. So the estimation of the model of the noise from 3 different collaborations are not fully consistent. In Parks, they hardly see any red noise component, whether in EPTA we see it clearly, and in nanograph, yeah, it's there, but very broad. So then you know information about gravitational wave signal only as good as you know the noise. And this is an important part. Moreover, yes, millisecond pulses are more or less similar, but nonetheless, they, like all people, we have 2 arms, 2 legs, 1 head. But we're also different, and so there are pulsars. And the noise in the pulsars also requires some careful study because there are some individual noises which are present in one pulsar but not present in another. And here is the list of the different noise components which we try to infer individually from the observation of each pulsar. So you see, I'm not going into details, but you see that 1713, for example, has a very long list of noise components, which maybe over modeling, maybe not, maybe it's not enough even. But nonetheless, what I'm saying is that each pulsar requires individual treatment like people. Okay, and it's very time-consuming work, which was not properly done, for example, in nanograph. They assume that all the pulsars are very similar. Next thing is the stationarity of the both noise and gravitational wave signal. I'm coming back to the signal which I'm almost done. Signal which was seen by Parks. And what they did, they were surprised why they see now what they didn't see before. And they they took 9 years of data and started shifting it by half a year and trying to evaluate significance of common red signal, which is basically part of the gravitational wave. And you can see the evolution here as they shift this 9 year. So there is clearly seen evolution of this. Another example, which I already showed you here, I mentioned with EPTA, because if you take 25 years of data, significance is very low. When we take the last 11 years, we suddenly start to see something. It could say something about gravitational wave signal, its evolution. It could say something about noise model that it doesn't cover full data and it has to be split by parts. Or it might say something about the treatment of the data and evolution of the instrumentation. So it's not that simple. And also I put this one, it's a comparison of Arecibo data and Green Bank. And you see they kind of agree, but not exactly. So if you're looking at, again, gravitational wave signal amplitude and gamma, look at the top and vertical one, orange compared to blue-green. So it's not the end of the story, in my opinion. In my opinion, it's not the end of the story. So what is next? Next, we're trying to combine all the data from all the detectors, all the collaborations together, and that's what's called IPTA, and that's why what main work is now going on. So there are data from 4 collaborations. In addition, we use precursor of SKA, Meerkat. They have 3.5 days of amazing data, and you will see publication soon coming from their own investigations. Very good one. And also CHIME is the Canadian radio telescope. We signed agreement with them. They will give us the data. So we will have more data, more pulsars. What is good about this? So we have better coverage in time. our data has gaps. It's not uniformly sampled. With more points, it will become more and more regular. It's still non-regular, but it's you bridging the gaps in the data. Then different radio frequencies of observations give you better measurements of dispersion measurement variations, which otherwise correlates very strongly with red noise, which we want to infer. And the most important, in my opinion, is we're not dominated by systematics, which could come specifically from each collaboration. Well, let's look at this. EPTA, most of the data, 65% comes from non-SAID data near Orléans. In the US, it's Green Bank. Parkes is a single telescope. Indian is a single telescope. So when you combine this data together, any systematics will be very obvious. And kind of summary, so what happens is that we think it is emerging gravitational wave signal. There are good, I think, rather strong evidence for that. In my opinion, it's not yet a detection. I think we need some work more. But we got so much excited that we've made huge noise and press release, and I'm here, as you see. But I think show must go on. And I think it's kind of, it's not chirp in LIGO, it's really a detection of gravitational wave in slow motion here. Thank you.
Thank you very much also for the good timing. And we have then time for questions. Well, I have a few, so let's start by you.
Thanks for the presentation. Let me try to formulate the claim. If I assume that I have a gravitational wave background, which would be isotropic, which would be unpolarized background and produced by a single type of gravitational wave source, and then I have the Ehlings-Down curve for the correlation, which is completely fixed, except for the value of a single parameter, which is the spectral index of the gravitational wave background, which is, I think, 13/3 for compact binary system.
Mm-hmm.
And what you say is that your data is consistent with that Ehlings-Down curve.
There are two statements here. We are consistent with Ehlings-Downs independently on the spectral index. Spectral index we are measuring separately, and the noise is consistent with Ehlings-Downs. And second is a part of what your statement is it consistent with the gravitational wave background from inspiraling binaries with 13/3? Yes, it is. It is.
But then would it be consistent with a gravitational background produced by cosmic strings?
Yes.
It is also consistent.
Yes.
And what is the value of the gamma parameter in that case?
That's the thing here. That's the constraint on tension, mu. But it depends a bit on it's between 10⁻11 and 10⁻9.5. G mu. This mu is a tension parameter. Well, this.
And this is for cusp or for kinks?
This is, I think, mainly there are several models into this. C is a cusps, K is a kinks, I think, and there is a combined one. We considered only, I think, cusps in here. And that's the guy who did this work, so you can ask him a bit more.
Marta.
No, next to Marta. No.
My question is on the slicing the data over time. So you show that both Parkes and EPTA have done it. For nanograph, you only show the difference between Arecibo and Green Bank. Have they tried any analysis over time or slicing the data in the same way that the other collaborations did?
I'm sure they did try it, but I did not see the final result of this. So they didn't publish anything. I saw the preliminary one, and there was some evolution. But again, when they see preliminary results, they could evolve a lot at the end. So at the end, I did not see the similar plot. Another my student, he's trying to fit non-stationary or mildly non-stationary model into this. Non-stationary, it's very hard to model. And he did see non-stationarity, but the base factor for this particular model was not very high. So I think current, probably not conclusion, but understanding it might come from the evolution of instrumentation. It's really, yeah.
But that's why, so in the case of nanograv, so the instrument, the telescopes have remained the same, but probably the analysis tools just at the telescopes have evolved over time as well.
Yeah, I'm less aware about the evolution of green bank, how instrumentation evolved there, but I'm more aware about the EPTA and parks.
There is another question here, and then I will let Julia afterwards ask her own.
I have two simple questions. I've heard that you can use astrometry to also look at a correlated gravitational wave background. What? Astrometry.
Astrometry, yes.
Position of stars. So do you think that we could use astrometry to confirm soon this result? Will it be competitive soon? Just because I don't know, what's your, do you know the status of that?
I know that possibility, and one of the scientific objectives of Gaia was to, by measuring, so similar effect to, let me just explain to similar effects. So here we are talking about delay in the arrival time, but similar effect you will have as aberration. So basically position of the star also affected by gravitational wave signal. And if it's noise-like gravitational wave signal, the position of the star should evolve in a similar way, for all the stars. Its effect extremely small, is even smaller than this one, but using 10 to the 6, 10 to the 7 stars, you might have something. I don't know the status, and I hope that yes, that would be interesting. Another interesting extension of this is using gamma observation of, it's not only radio, which you see this, but also gamma. And in gamma, you have free of dispersion measurements. So basically they propagate, they're less affected by dispersion. And we're trying to also now bring gamma observations from into the game and do radio and gamma together.
Okay, thanks. The second simple question is, we talked about significance of all these different independent measurements, they seem to be to me. Can we combine all of them in one statistical analysis? Because if I have a lot of 3 sigma detection, then if I put them all together, it will become a 5 sigma detection.
Yes and no. Yes and no. Yes, and that's what we're trying to do in a nice way by using IPTA, by putting data together, okay? No, it's because, I give you one reason why not. Because our noise models are not consistent, for example. Our noise models are not consistent, so simply adding things together does not work. And the whole idea of IPTA is to basically bring the data together. There is another reason. It's a timing model. Actually, it's interesting when you're combining data from 3 collaborations or 4 collaborations. Your timing model, so basically measuring parallax, measuring dispersion, slightly start changing, okay? That's another reason. So you dealing with, at the end, with slightly different data at the end. So because what you're doing is, you have observation of time of arrivals. You're trying to fit or understand the timing model, subtract it, and then you get residuals. But because your timing model is slightly different, your residuals will be slightly different. So just simply a naive combination, it does not work that well. But we hope that by proper combination, we will definitely go to 5 or 6 sigma result.
So you really have to go and make the effort of having a model.
That's my opinion,
all
yes,
the observations.
Yes. But there is an attempt to do what you said in one of the papers, but they didn't claim any significance, but they're trying to naively, or at least minus first approximation, to do this kind of combination.
Thank you. Next question was from Julia. So Julia, you can ask your question if you like.
Thanks. Hi, Stas. Thanks a lot for the nice, very nice.
We can't hear you. Are you around?
Yes. Can you hear me now?
I'm walking towards Christophe, but maybe.
Hello. So my question is very naive. It used to be that the slowdown of pulsars was one of the best ways to measure a fundamental constant with high precision. Now you are looking at correction to this, does that mean that the kind of measurements you're doing is better than anything else has been done in terms of precision, or are the two kind of measurements independent?
In a way, two are independent. So you're assuming that all the slowing down of the pulses come through your, it's basically a question of modeling. How you define your, how do you explain your slowdown? One of the parameters which we fit indeed is a slowdown, and it's also but for us it's nuisance parameter. We're trying to fit it and we're getting rid of this, okay? And we're fitting it within an assumption of general relativity and very simple ones. And then and whatever residuals you're assuming that they're through gravitational waves and noise. You can invert other way around and saying there is no gravitational wave, what else could it be? And for example, another thing which is not gravitational wave is dark matter. I'm not mentioning it here, but if there are potentials of the dark matter, they also could create, blue and red shifts of in the propagation time of arrivals. And one of the investigations which was done is exactly constrained on the homogeneity of the dark matter in the universe. So it's a question of really how you model your data.
But for this community, what you are looking for was their noise, right? So it means that the amplitude of your noise was so small that they didn't need to worry about it, or because it had a different spectral signature, they could marginalize over it, or?
For the timing model, yes, we're marginalizing over this, yes. Okay. Yes, exactly.
Okay, so Julia cannot speak, but she wrote her question, so let me read it. Can we do mapping with PTA? For example, assuming the signal is due to cosmological background, how a kinematic dipole would manifest itself in data?
How what?
How a kinematic dipole would manifest in itself in data.
I'm trying to so for this, you would need to do specific investigation of anisotropy in your background. And this can be done in a similar way as it's done for CMB. So it's not very sensitive to higher multiples, but in a dipole, for example, in principle, you should be able to see. But my example of continuous wave is preferred direction in some sense. And ability to look at anisotropy or preferred direction in a purely background are very limited, because even for the isotropic component, which is supposed to be strongest, we don't have certain information. But if you, on top of this, if you're trying to see the anisotropy, it's not that simple, unless it's very strong. But even example of continuous wave, it's basically preferred direction in the hot spot, preferred direction on the sky, on the isotropic part. And even that was hard for us to differentiate whether it would be there or not. So I presume that in principle, we might be able to do that, but not with the current data. And you need some additional investigations by doing this decomposition of the sky and then the harmonics and trying to see specifically for the dipolar part.
Okay, thanks.
Yeah, that would be my answer to this.
Okay, thank you very much. I think it's exactly time to stop. Thanks again.